Okay, so bringing together what we've learned so far, this chart shows us all the energy involved in, for instance, starting with 1 mole or 18 grams of water ice at negative 25 degrees Celsius and heating it to the point where it's the same mass of 125 degree steam or water vapor. Strap in because there's a lot going on here. First, as we add energy to the ice, its temperature will increase until it reaches its melting point of 0 degrees Celsius. The amount of energy required to raise the temperature is given by the specific heat of the ice times its mass times the change in temperature. Hopefully that'll ring a bell from thermochemistry in Chem 1211. If not, stop this video and take a few minutes to quickly review specific heat, and this can be found in Chapter 9 of your book. Once the ice reaches 0 degrees, adding energy no longer results in an increase in temperature. Instead, the energy is used to break apart some of the intermolecular interactions between water molecules in the solid until all of the ice is melted. The amount of energy required to do this is equal to the enthalpy of fusion multiplied by the number of moles, in our case, 1 mole of water. Once all the water has melted, we now have liquid water at 0 degrees, and only now will adding more heat energy result in further increase in temperature. The temperature goes up until we reach our next phase change temperature, which for water is at 100 degrees when it will start to boil. The total amount of energy needed to heat the liquid from 0 to 100 degrees is again the specific heat of liquid water times the mass times the change in temperature. The specific heat of a substance depends on its phase, so the specific heat of liquid water won't be the same as the specific heat capacity for ice. Next, we reach the point where adding more energy to liquid water at 100 degrees Celsius won't result in any further increase in temperature of the liquid. Instead, the liquid will start to boil until all the water has vaporized. The amount of energy required here is the enthalpy of vaporization multiplied by the number of moles. Again, rather than being used to raise the temperature, the absorbed energy during the phase change goes into breaking apart the intermolecular forces in the liquid. Finally, once all of the 100-degree water has been vaporized, we can raise the temperature of the resulting steam by a further 25 degrees to 125 degrees Celsius by adding more energy. Just like the previous two times where we raised the temperature, this amount of energy is given by the mass m times c, the specific heat capacity, times delta T, the change in temperature. Here's a list of enthalpies of fusion and vaporization for some common compounds. These are all empirical values, so they'd be provided for you as needed. As you'd expect from the explanation on the previous slide, you should be able to notice a correlation between larger intermolecular forces and larger enthalpies of fusion and vaporization. This is also why strength of intermolecular forces correlates with increasing boiling point. Okay, knowing what we do about phases of matter, let's look at what are known as phase diagrams. These aren't terribly difficult to understand, but there are a few terms to know as we look at them. The normal boiling point is the temperature that a liquid boils at when the external pressure is exactly 1 atmosphere. Likewise, the normal melting point is the temperature at which a solid melts under the same 1 atmosphere of pressure. Something that might seem a bit strange is the triple point, which is the specific combination of temperature and pressure at which all three phases of matter coexist in equilibrium with each other. We'll look at an example of this in just a bit. Weirder still is the critical point, the specific combination of critical temperature and critical pressure beyond which a gas cannot be liquefied by increasing the pressure. The unusual state of matter that exists beyond these conditions is called a supercritical fluid, and it's so strange that I'm actually going to have to insert a video clip later to give you an idea of what it's even like. Now that you're familiar with these terms, here's the most common phase diagram you'll come across, which is the phase diagram for water. The orange region represents all combinations of temperature and pressure that result in solid water or ice. The green region is the liquid, and the blue region is where water is a gas, steam, or water vapor. Beyond the labeled critical point, you can see the region where water is a supercritical fluid as well. For any given temperature and pressure, we'll find ourselves at some point on this graph. Moving left and right correspond to decreasing or increasing the temperature, respectively, and moving down or up correspond to decreasing or increasing the pressure. If you look along the white dotted line at 1 atmosphere of pressure, you can see the boundary between solid and liquid water occurs at 0 degrees Celsius. So this is the normal melting point of water. Likewise, the boundary between liquid and gas intersects the dotted line at 100 degrees Celsius, so this is the normal boiling point of water. At a very low pressure and just above 0 degrees Celsius, you can see the triple point, where all three phase boundaries intersect. Notice that at even lower pressures, the liquid phase no longer exists. We can only have ice or water vapor. Other important features of this graph are the boundary between liquid and gas changes dramatically depending on the pressure. The lower the pressure, the lower the boiling point, and vice versa. This is typical behavior for virtually all liquid substances. For water in particular, the phase solid-liquid boundary has a negative slope. This means increasing the pressure lowers the freezing point. This makes sense if you think about it. Ice is less dense than liquid water, which is why ice floats. So if we take ice at its melting point and compress it, increase the pressure, it will want to become the higher density phase, which for water means melting into a liquid. This behavior of water is actually highly unusual. Water is one of the relatively few chemical substances that actually has a less dense solid phase compared to its liquid phase. When almost anything other than water freezes, its density increases and it will sink if placed in a container containing the liquid phase of the same substance. This unusual property of water, where its solid has a lower density than its liquid phase, is due to the ordering of water molecules in the liquid phase that arises due to its strong hydrogen bonding interactions. This next phase diagram is for carbon dioxide. A couple notable things here. First of all, standard atmospheric pressure is around 100 kilopascals, so if you look at that region on the graph, you can see that this is lower than the triple point pressure, which is about 700 kilopascals. Hence why dry ice sublimes. The pressure would need to be much higher for it to be able to melt before becoming a gas. We can also see the much more typical behavior of a positively sloped solid-liquid boundary. Carbon dioxide, like most substances but not like water, has a higher density as a solid than it does as a liquid. Finally, the critical temperature is at about 30 degrees Celsius, which means it's possible to witness the transition of carbon dioxide from a liquid or gas to supercritical fluid at a pretty everyday temperature. Here we can see examples of some of the weird stuff on the previous diagrams brought into actual physical reality. On this first slide, we have a flask of water hooked up to a vacuum pump to reduce the pressure inside down to the triple point pressure. If you look closely, you should be able to see both bubbles and chunks of ice in the liquid at the bottom of the flask. As predicted by the phase diagram, but very much counter to our everyday experience, the water is boiling and freezing at the same time. Here's a seemingly magic phenomenon that isn't so astounding after all if you understand the phase diagram for water. We have a big block of ice and two weights attached to either end of a piece of metal wire draped across the top of the ice block. Because the wire is pushing on the ice block with the force of the weights on either side of it, the pressure between the wire and the ice block is relatively high. That, in accordance with the phase diagram for water that we saw, causes the ice directly underneath the wire to melt and allows the wire to slowly pass through the ice. Once the wire passes through any given part of the ice, the water that is now above the wire as it moves down is no longer subjected to that higher pressure, and so it freezes again. The result is that the wire slowly cuts through the ice block without ever actually breaking it apart. At the end of the experiment, the wire has passed all the way through the ice, and yet the ice block is still in one piece. And here's a short clip of some liquid and gaseous carbon dioxide in a high-pressure chamber. As it warms up past the critical temperature, the boundary between the two phases simply disintegrates, leaving us with a supercritical fluid. If we then take that supercritical fluid and cool it down below the critical temperature, it once again splits apart into separate liquid and gas phases. I don't know about you, but this never ceases to amaze me. What on earth have you ever seen before that behaves like that? Finally, let's take a look at another unusual phase of matter, liquid crystals. You've probably heard of these before, whether you realize it or not. LCD screens? That stands for liquid crystal display. These things have a lot of applications in TVs, computer monitors, etc. The liquid crystal phase is an intermediate phase between solids and liquids that exists for only a handful of substances. Instead of simply moving from an ordered solid phase into a randomly oriented liquid phase, the solid first transitions into a liquid crystal phase, where the molecules can move around like they would in a liquid, but remain oriented like they are in a solid. Further heating produces a conventional liquid phase. Here you can see a diagram of a molecule of a compound that can form liquid crystals. As you can see, different portions of the molecule give rise to a combination of intermolecular forces, rigidity, and structure that make the formation of the liquid crystal phase possible. There are actually a few different types of liquid crystalline phases, shown here. Nematic liquid crystal phases have the molecules in parallel orientation, but not aligned end to end. Smectic liquid crystalline phases are aligned both parallel and end to end, and cholesteric liquid crystal phases have the molecules aligned in parallel planes rotated at an angle to each other. One application of the cholesteric liquid crystalline phase is that the angle of rotation often depends on the temperature, and furthermore, the angle of rotation here also determines how the liquid crystals reflect light. If you've ever seen one of those thermometers attached to the side of a container, usually a fish tank, where a color pattern appears at a certain point on the strip to indicate the temperature, it's exploiting a cholesteric liquid crystal phase to display that temperature. So that brings us to the end of Chapter 11. Hopefully I'll see all of you in class next week, and in the meantime, please reach out via email or, better yet, drop by my virtual office hours on Microsoft Teams if you have any questions. Take care.